Okay, so my name is A.J. Guillon. I'm actually an alumni from the University of Toronto where I did computer science, and I wound up getting invited to join the Kronos group to actually work on the OpenCL spec. So I've been doing GPU programming long before it was cool. So my initial dream or passion was to become, a nuclear engineer or something like that because of this thing. So, there's many scientists in the room, and there's a certain percentage of us started with Star Trek, right? So, this was kind of where I wanted to end up, but computer science kind of drew me in, and I'm in good company. Dijkstra started out as a physicist, became a computer scientist. There's a number of people in the field who started out in physics, and computer science is kind of a young field, still emerging. We're still figuring things out, and so there's a lot more excitement to work on that than to go and try to figure out, an unknown problem that there's been no progress on for 200 years or something like that. So I wound up here, and this is my hometown of Barrie. So further up north. Technically, the company I work on is headquartered there. This is called a PR campaign, just to show a picture. So it's like NASCAR. You have to show all the logos. This is what takes most of my time right now, is figuring out how the heck to program a modern GPU. And when I say GPU, it could also be an FPGA or other accelerator like a Xeon Phi or something like that. So that's the whole kind of point of the OpenCL standard. Today I'm here to talk about memory models, but a lot of my time goes into figuring out how to make parallelism work from the point of view of a computer scientist. So if we continue the Star Trek analogy, I'm kind of like Scotty or LaForge, you're in the back end, you're trying to make sure that everything's just kind of working, and if you need more compute power, you just buzz down and I'll make it work for you. That's basically what my background is these days. So this is how it actually feels to write a specification. I don't know how many of you have been involved in standards bodies, and Kronos actually is very good, but this is how I often feel when we talk about memory models, or we talk about all these different things. And you can tell from this room that we have a mixture of users, we have a mixture of computer architects, and I think I'm the only software engineer / computer scientist in the room. Oh, we have another one. So it's kind of a mix, right? And what we're going to talk today about is how the memory model makes all these pieces basically fit together. So the world today is completely parallel. Nobody wanted it to happen, right? So I'll show you some illuminating quotes. This is Donald Knuth. He said, "I decided long ago to stick with what I know best. Other people understand parallel machines much better than I do. Programmers should listen to them, not me, for guidance on how to deal with simultaneity." So this is one of the main people in the fields of computer scientists, one of the most popular computer scientists alive today, and he's basically put up his hands and giving up on parallel programming. So it doesn't sound good if your only job is to do image analysis or model an atom or something, that the people who are supposed to have figured this out for you just put up their hands and said, forget it, we're out of here. Tim Matson, who's a former CEO of OpenMP, he's quite popular, said, "We stand at the threshold of a many-core world. The hardware community is ready to cross this threshold. The parallel software community is not." So we all know that parallel programming is a thing. The computer architects in the room, if you could just make our processor run a little bit faster sequentially, we'd be much obliged, but I don't think it's actually going to happen. So parallel programming is so hard that when people aren't busy Ubering or selling, their spot in line or something like that, Y Combinator actually has listed solving parallel programming as one of the most friendly, ambitious startup ideas that actually make you a billionaire. People don't make these statements unless a problem is hard, right? So you will meet people who say, yeah, this is a solved problem. Well, they should IPO, right? If it's solved, you're in pretty good company. OpenCL doesn't solve the problem either. But today we're talking about memory models. So Herb Sutter says, he's a chair of the the ISO C++ Standards Committee, "Everybody who learns concurrency thinks they understand it, ends up finding mysterious races they thought weren't possible, and discovers that they didn't actually understand it yet after all." So the memory models is one of the most complicated pieces of technology to ever be developed. And we're only going to motivate it. We're not going to talk in detail about it. We're going to talk about why it's difficult, but we're not going to get into a lot of detail. So there's a lot of false solutions in parallel programming, right? There's lots of people who claim that parallel programming is a solved problem, but they never actually tackle the general problem. They're generally tackling a subcase that does have a well-defined solution because everything kind of factors out and it just collapses and it's easy, right? It's like assuming a frictionless surface, the world is a perfect sphere, cows are spherical, and all of these types of things. By the time you add these assumptions, you're not actually modeling real life, and you've convinced yourself that you have, and any bridge you make will then fall down, right? So this is one of the issues with parallel programming, is we don't even know how to deal with parallel programming, right? In terms of what the general problem actually is that we have to solve, it would take an entire course or workshop to solve it. So Marcelo attended one of my training. He can fill you in one lunch or something like that. So it is very difficult to even describe the nature of the problem in general. And it's pure theoretical computer science. So it is a matter of perspective. We're looking at this, you can tell from this room, everyone's looking at parallel programming and supercomputing from all different angles. So computer scientists say, parallel programming, this is way too hard to figure out. Now the computer architects, if you don't want to lose our business, go fix our problems for us, right? That's kind of the computer science approach right now. Computer architects say, look, we've reached physical limits. This is what we can do. We can't do any more. You figure it out, or you're going to lose your business. And software engineers will tell you, parallelism, you just mean like a lock, right? So we're kind of in the situation that everyone's talking past each other. The analogy I make is it's kind of like the channel, the English channel where they're building this kind of tunnel to connect, England and France. Well, one end of ours ended up in Australia and the other one in Hong Kong. Like, we totally missed. And you're going to see why it's actually the memory model that's the fundamental problem. So parallelism is a really big deal. Now, HPC is a field that I actually have two acronyms for what HPC actually means. The first one is hocus pocus computer. That's one definition, right? Hocus pocus computing, this is easy, everyone's dumb, we got it figured out, we got it. We bought a big machine, easy. There's also high performance computing, which is, look, we have to figure this out. We're doing an image, we're trying to study cancer, we're trying to study relationships, we're modeling something, so we're going to actually figure out how to make this work, right? Unfortunately, it's difficult depending upon who you're talking to, which camp people are in. Here at SciNet, we're mostly in the high performance computing business, but there are people who will say, oh, this is finished, I bought a supercomputer, done. This famous lore, when I was finishing my undergraduate, it wasn't at this institution, it was another university. Physicist bought a big, at that time it was an alpha cluster, installed their sequential Fortran program, turned it on, and it was no faster. And then complained to the vendor, right? So it's one of those situations where we actually have to do something to get this performance. And what we have to do is parallelism. But what I'm going to show you today is that actually the memory model is so intertangled with parallelism that we can't separate the two. So today, this is a really big issue. The entire IT industry, it's worth what, like $2 trillion or something right now? I mean, it goes up and down, but it's bet its entire future that programmers will finally successfully switch to explicitly parallel programming. And we really don't know how to do it, right? So that's parallel programming, and you're going to see that in some ways it's a little bit easier than the memory model, in some ways it's a little bit harder. It's actually a foundational piece. So we're going to talk about Bewitched, right? So one approach to solve this problem is just to rely upon superstition and hope and magic, and maybe it'll just go away. And we'll see what happens if we wind up doing that. So parallelism, there's many flavors today, right? We could have SIMD lanes, single structure, multiple data. You can have hardware threads, software threads. You can have multiple cores, so one processor has multiple cores inside. You can have multiple devices of different processors. This is basically called heterogeneous computing, basically have different ISAs on each of these things. This is what OpenCL is about, right? And OpenCL is the only spec in existence that's about this. I think HSA does some of this stuff as well, but really this is OpenCL is the dominant standard right now with everyone at the table. You also have clusters, right? SciNet has a cluster. What SciNet, I don't believe, has is a distributed system, right? We're going to have a data center here and a data center in Singapore and a data center in Sweden, right? That's a whole different thing. But these are all different flavors of parallelism, right? So there's also many flavors of data exchange. We have message passing, people who be familiar with MPI, and we also have shared memory approaches. And you can do hybrid approaches between those. I think people here, I'm sure that a lot of the people in SciNet in this room have done this type of stuff, where you have a mixture of shared memory and message passing in the same application. And in many ways, from the theoretical perspective, shared memory and message passing are actually equivalent. So for example, the MESI protocol, computer architects can explain it to you. Well, we should have got you like t-shirts, right? But this is built essentially using message passing, right? So you can basically interchange what you build on top of which. So you can implement shared memory using message passing, you can implement message passing using shared memory. So from the point of view of a computer scientist, these are somewhat equivalent. So the whole idea of parallelism, what we really want is that if you have a program that executes in time t and you have p processors, you want to execute the same problem in t divided by p. So we don't actually even know if this is true. Okay? There's no foundation in computer science that says this always happens, right? It's a very complicated problem. There are examples where it works, where it's embarrassingly comparable, and in general, we don't actually have solutions. So what's changed, right? So from the software engineering standpoint, the vast majority of practices do not hold in parallel systems, okay? So users at SciNet, users at HPC sites, you're gonna pick up a book on programming, and that book's gonna say, here's a whole catalog of approaches or patterns, if you wanna sound cool. This is how you write applications. Well, the people writing those books have no idea how to figure this out. In fact, the entire field doesn't know how to figure this out. And there's a few reasons for it. So number one is we have complexity notation, asymptotic complexity. Probably familiar with this, big O and stuff like this. It doesn't really work in parallel. So when we estimate runtime of an algorithm, we basically count the number of instructions that execute as a function of input size. So it's reasonable in sequential systems because memory access is bounded by a constant. In parallel systems, it's actually a function of the number of units of execution that are concurrently accessing that space, right? So because it's no longer constant, you actually wind up with all sorts of craziness when you look at how you might be able to, actually no, you can't even bound it, but that's not the topic for today. So we're in this position that we can't even analyze how effective a parallel algorithm actually is. And contention affects your performance. That should have changed the slide. It should be software engineering. Oh, we'll call it software engineering with OpenCL. This is a reuse slide, as you can see. So when you have composability, right, we have the ability to use a feature without regard for other features being used in your program. So I have F is correct and G is correct. Maybe you wrote F and you wrote G, and I'm just going to use the two of them together. You can't actually do this in parallel. The implications for software design are enormous because this means that I can't just pick up something that Marcelo wrote and call it. Right? Not unless there's a lot of layers of compatibility, right? So sometimes it may generate incorrect output, and sometimes it might have so poor performance it's completely useless. And part of it is that you actually can't hide how parallel systems represent, how they interact with the world. So you might be able to compose, for example, maybe something's written in OpenMP, and you can call other OpenMP things. You can't call an OpenCL thing and expect it to work. And when you get into C++, you can't expect, based on the memory model being used, for them necessarily to be composable. So in general, it doesn't hold. There are special cases where it does, but in general, it doesn't hold. So this violates modular design because you actually have to know how a lot is parallelized, and this violates information hiding. This is one of the most precious notions of software engineering, right? And it does not hold. So we're going to start anyways. I mean, this is kind of painting, we don't know what's going on with parallelism, but there's a lot of motivation. We have to find a solution. So we're going to start at the basics, right? Where do we start? We start by defining a memory model. So the first thing we're going to describe, the big lofty goal, we don't know how we're going to do it, but we're going to start little pieces. We want to go to the moon. Well, we don't know how we're going to do it, but we can start by building rockets that blow up on our face continuously. And you'll see the memory model actually does that right now. But no, everything gets started. So we're going to go ahead and we're going to start to build a solid foundation so that whoever does have that solution to parallel programming in general can build on top of what we've done. So that's exactly what the memory model is all about. So computer scientists have to worry about what instructions and types of memory need to be in the ISA. So the first thing is, if you don't have instruction X, maybe you can't even call yourself a parallel machine. Maybe whatever you have is not going to continue to scale, and this has happened. There are very important results relating to the types of instructions you need. So computer scientists have spent their time figuring out what primitives you need, how memory should behave, etc. Oh, it's double-sided. Very fancy. So the question really fundamentally is what happens, how does memory behave when you have multiple reads? Multiple things are reading memory at the same time. How does memory behave when you have multiple writes to the same address, right? Or even related addresses. So element X of a struct and element Y of a struct. Is it okay to write them at the same time? What does it even mean? So simultaneity is really confusing, but without a memory model, we actually can't say anything. If we want to mix reads and writes, what does that mean? So one of the theoretical results that we're not going to go over, obviously, but one of the important theoretical results is that a register providing only compare and set operations has an infinite consensus number. So there's a little bit of theoretical computer science. We can talk about it on a whiteboard, but this has an implication for how you build architectures. And what those implications are, based on my understanding, is that if you want to have a weight-free algorithm, which is basically the fastest of the fast, the weight-free algorithm executes in a finite number of steps independent of the number of processors, right? So if I have 1,000,000 processors, it'll take just as long as if I have 1 or 2. It's a very desirable algorithm. It's the only thing that really scales. So in order to get such an algorithm, we have a mathematical proof that you have to have an atomic compare and swap. So your ISA had better have one, right? So this is a type of things that we're doing in computer science right now, is determining what instructions you need to have so that you actually can scale, because you don't want to limit yourself based on how we actually have abstracted the machine. So the hocus pocus computing solutions, which we never will use here, is that you just rely on magic, potions, runes, numerology, anything it takes, and we're just going to imagine it's just going to work how we expect, and we're going to completely disregard computer science, or we're going to disregard computer architecture because we're too smart. SMRT, right? So that's one solution, and we would never do that, right? Because this is poor science, this is pseudoscience, right? So, I mean, it's easy to say, oh, there's no problem, everything's figured out. You know, what's everyone's issue, right? So there's a lot of, you know, I'll say this background that the memory model that we have today took 30 years to develop. A lot of that time was convincing people it was worth doing, okay? So now that we have kind of this, we've decided to move away from superstition and actually say we want to actually describe how our systems work. We actually want to come up with something. How do we do it, right? So now we decide, okay, we want to take action. And I'll show you examples towards the end in terms of things you think will work that actually won't work, in terms of why memory models are important. So this is a data race. This is OpenCL. You can do the same thing in any language. You basically have two threads, whatever they are, okay? Each work item in OpenCL language will grab an index from the space, okay? Thread ID or whatever it's called in CUDA. And everything's going to try to write to one memory cell its index, okay? So what's the final result of this operation, right? So if I have work item 0 is going to write 0, work item 1 is going to write 1, okay? And this is, you could extend it to n. What's the final answer? What do you think the final answer is going to be? It's completely undefined. So there are people who will say, yes, but I'm going to exploit this trick and I think it's going to work. One of the famous tricks people like to do is a volatile keyword from C, which actually has no meaning at all in parallel, which is meaningless, right? But people will try it. And they'll say, well, this fixed it. And then you just kind of, 1, 2, 3, 4, it's fixed. It's all superstition, right? So this is completely undefined behavior. The way the memory model works is we basically say that if you ever do this, there are no guarantees in terms of what's going to happen. The hardware doesn't know, the compiler doesn't know, your application is a completely undefined state. So very important definition. If you don't have this definition, you actually can't construct a memory model, right? So first definition is never have a data race. You can never have a mixture of reads and writes at the same locations simultaneously, ever. So we know that. I mean, that's why we use locks, right? We might think that it might be one or the other, right? It's actually completely undefined what happens. It might happen that you get one thing at one point. It might happen that you segfold. It might happen that every nuclear missile in the world launches. You have no idea what's going to happen, right? So we define the data race as actually completely undefined. So, you know, again, we're looking at, okay, well, we can't define, you know, we have to do something about data races, so we can't have them. But whose problem is a memory model, right? Can we stick it with someone else? Can we make it someone else's issue? So can the OS, you know, we're not going to change our code. That's too precious. You figured out, you're the OS vendor. You know, can we do it there? Can we make the processor fix things so we don't have to have a memory model? And so on. I mean, it's always popular to kind of move the problem, right? And there was a little bit, if you look at the history of defining these things, there was a little bit of this going on. You know, where should the problem actually be addressed? And essentially, this is all just saying I don't want to change anything, right? So people also say, okay, look, you know, we know we have to have a memory model, but can we avoid it? I'm going to avoid the problem in this way, right? So we still don't have anything formally defined. We're just going to play all sorts of tricks and try to get around it. So people at least are no longer avoiding the issue, they're actually confronting it, right? So we have this issue that we don't actually know what memory does in parallel whatsoever, right? We have no idea. We have all sorts of ideas, but we're just going to try to avoid it, make it something else, add the minimum amount of language to the specification and so on. So eventually the industry came together and said, okay, we're going to fix it. We're going to involve computer architects. We're going to involve all the major processor companies, software companies, computer scientists. We're going to try to figure out what the memory model should be. And honestly, this is laying down the next 50 years of architecture, right? So this initiative just recently completed. Any idea in terms of when this was actually done and how long it took? Any guesses? Sorry? 20 years? It was 30 years. So when do you think it was finished? It just happened in 2011 that we have C++11 that has a memory model, okay? And we're going to talk a little bit about what's inside of there. So the general idea, and this is very important to anyone doing parallel programming, is that whatever this answer is, any solution to parallel programming is going to rely upon this foundational piece that we have a memory model now, right? This is a very important piece of the puzzle. So we don't know what the final solution is, but we're going to have the memory model so that we can add support for it. And this was a major initiative because even though you might be running just on Intel x86 right now, well, you might be running on Itanium later, you might run on Alpha, you might run an FPGA, you might run in a GPU, so you have to have a definition that works for all processors. And that's where OpenCL came into the picture. C++ did it for CPUs. And then OpenCL extended those general ideas to other architectures. Okay.
Yeah. Comment or question from viewers you prefer to
Can we do it at the very end?
Yeah, sure.
So parallelism and memory models turn out they're completely inseparable, right? So if you get nothing out of this presentation, just remember, if you're doing parallel programming, unless you never ever cooperate with memory, you have to bear in mind the memory model. So it turns out as well that we've kind of been living a lie as computer scientists, computer programmers, and the programs we write is not what's ever executed, right? We write a program, but the actual system doesn't understand C, doesn't understand C++, okay? Instead, there's many layers of things that are going to transform that. You're going to run an equivalent program. So the compiler will take your source code and will generate an equivalent program and then pass it to the processor at compile time. At runtime, the processor will reorder instructions on you and generate an equivalent program. But don't worry, we promise it's going to be faster, right? Everything is doing these transformations in the interest of speed. So you get transformations at compile time, you get transformations at runtime, right? Now in parallel, we're going to realize that we actually have to have a new notion of equivalency. It's one of the major contributions of the memory model. So it's the memory model that provides the rules for what processors are and are not allowed to do. And not just processors, the compiler, etc. So we'll go in a little bit of detail in terms of what this kind of thing is. Bjarne Stroustrup calls the memory model a contract between software developers, compile architects or compile engineers, and processor architects. So memory model is a contract. Software developers, we have to agree. Our only job in this is that we do not have a data race in our program, and we follow the word of the law. We're not breaking the law, okay? And compilers actually can't determine if you're breaking the law. It would be the halting problem. It's actually incomputable, right? So we have to promise, we guarantee you, compiler, we can guarantee you we do not have a data race. If you obey this contract, then the compiler agrees to optimize only in ways that do not violate said memory model. So it might generate an equivalent instruction, it might do all sorts of things, but will never violate the model. And processors agree to not violate said model, okay? So it's a contract written, it's like a bunch of pirates coming together on the island and it's signed in blood type of thing. There's like a Garfield Halloween special, right? Everyone came together and said, look, we are not going to violate this. So this is recently just came out. I mean, the OpenCL 2.0 memory model was released in 2013, right? Which took a long time to develop. So the work that was been done by C++11 has now been adopted by C11. It actually had a mistake in it, right? So even though we're talking about memory models, we haven't really seen much. Think of it that some of the best people in the world working on this full-time for years wrote a specification that had a tragic flaw. So what hope do you have if you're trying to write a for loop or something like that this is the situation you're in, right? And we'll talk about that a little bit. But the mistake is corrected, I believe, in C++ 14. I'm not sure. I've been following C++ for a little while. And OpenCL 2.0, the biggest feature is that it has a memory model. So if you don't have a memory model, absolutely nothing works. You cannot even implement a mutex. You might say, I'm going to avoid this issue by having a mutex. How does a mutex work? In order to work, it has to have a memory model, right? So no one is imagining that you're going to go and write all of this low-level code. It's an idea that in order to provide high-level constructs, you're going to have these pieces. So here's well-defined, here's well-behaved code, okay? So in this piece of code, we basically have a Boolean that just checks, if you have a lock. So have lock equals false, and then while you don't have the lock, you're going to spin until you obtain it. And when you have the lock, you're going to say y equals 33, and then you unlock, right? People have probably written code like this at some point. So what do you think this code actually does, right? So there's absolutely no way without a memory model to tell what this code does. It may sound really weird, but the compiler is completely allowed to do this. It can say, look, we have y equals 33 under here. There's no dependencies in this function. So we're just going to put that there. And then we're just doing the lock and unlock as an exercise in futility. This, as far as I know, is completely valid. The way to make this invalid is to define a memory model, right? So this is the type of stuff that happens. Even if the compiler doesn't do this to you, you turn off optimizations, the hardware might reorder it in out-of-order execution because it does not know that this thing is a lock, right?
I have a problem so far.
Can we leave to the...
No. I need to know what a memory model is.
You're going to find.
Okay.
So this section...
You've been mentioning that to 200
Exactly.
times.
Well, it's very important. So the presentation is structured like this. First, we're going to rely upon magic. Okay, but we've decided we're not going to do that. Now we're going to say we're very upset, and then I'll show you the solution. Okay, so first we're still saying like we're upset because if you are bothered, then you are the perfect example. I don't know this person. I've never seen him before. He's not a plant. Okay, so that's exactly, this is a perfect effect. Okay, so the memory model, OpenCL 1.x. Some people have written OpenCL code. Okay. I have an initial state, x equals 0. This is some sort of global variable, right? And I have two work groups. Each is going to do an atomic increment of this. What's the final value? Okay, so atomic increment, is indivisible. You can mix read and writes of atomics. So I'm going to increment in one work group and increment in a second work group. How many people think the final value is 0? 1, 2? Impossible to say. So it's actually completely impossible because we don't have a memory model, right? Even for atomics, we don't have a memory model. So the OpenCL 1.x standard has no memory model at all. Even atomic operations are a little bit fishy in terms of what they do. And it turns out, and in my opinion, this was a little bit of a mistake, that OpenCL atomics aren't actually atomic. So, that's a kind of technically, if you read the specification very closely, it says that atomics are only valid across a work group, okay? But the specification is a little bit ambiguous. So stay tuned and I'll probably write up a blog or something like that, or an article about what actually means, what's going on. So the consequences are, for 1.x, that if you strictly follow the spec, okay, your atomic increment, you're just implementing a histogram, that's not even guaranteed to work, okay? And you follow the spec, okay? So this is because, again, there is no memory model. And is it really that bad? Well, technically, we had many parallel programs before we ever had a memory model, before we even had a notion that it was something we needed to have, right? So that is something that people will still do this, but the people who write parallel code without a memory model have to check the generated instruction sets, the generated instructions by the compiler, disassemble it, make sure that they completely understand the architecture of the system, and then reason about that. There are very few people in the world who can do that, especially for all the different architectures out there. So with a memory model, you don't have to worry about it. So now we're actually going to talk about memory models. And the memory models are completely bewildering, right? So if you thought the past was confusing, this is even more confusing. So we need to have a memory model. We create one, but the result is a little bit hard to understand. So we have a memory model. OpenCL 2.0 has one. What's inside of the memory model? Well, inside of the memory model is a number of relations, okay? We define something called program order, which says basically what it means when you write code. You write a C program and it has an order, if this, then do this, and so on. The compiler people and the hardware people want to be able to reorder that. So there's actually a definition of what program order is that allows a little bit of manipulation, okay? So inside is a formal mathematical definition of program order. We also have a formal definition of something called synchronizes with that says that when I have a write, someone will eventually read it. And that's the one that does it, okay? So you have a connection between multiple processors, and you have happens before, which says this is the total order in the history of the execution. And the point of the memory model is just defining what these equivalencies are. And once you can reason about this, then you understand how to structure code. One of the other issues is that because it's a committee, we don't just get one, we actually get many memory models. So there's two extremes, okay, depending upon who you are. One extreme is sequential consistency. So what this means and this was done by Leslie Lamport in the end of the 70s, is that, so we agree that we need to have some common view of memory, okay? And I have one process, I have another process operating. So sequential consistency is that the memory operations maintain order, but they're just interleaved, okay? So one way to think of it is that your memory is attached to a switch that just connects to different programs. When it runs, it's going to interleave in a well-defined way. So a way to think of this is that if you have a bunch of people in one line wearing red shirts and a bunch of people in another line wearing blue shirts, it doesn't matter, they can just you can intermix them however you wish, but you're not reordering the people, right? Not reordering them from their line. That's exactly what sequential consistency is. The other hand, we have relaxed consistency. These people that are standing in line, and maybe they have numbers painted on their shirts, can jumble themselves up however they wish and then intermix. Okay, so relaxed consistency is this extreme where nothing is promised, right? The ordering is completely relaxed. Processor companies love this because you just throw in some stuff and there's very few rules. Program order is completely violated. So computer scientists, we have this notion of sequential consistency. Okay, and here's one of the issues with where we are in the industry right now today. Okay, computer scientists said, okay, computer architects in the room, you have to implement sequential consistency, but we're going to give you the relaxed consistency model, which is what you want. So as a side note, the computer scientists, I don't even understand why we want this thing, but we want sequential consistency. Relaxed memory consistency, architects will say, will give you orders of magnitude more performance. So obviously they want that one, right? And because they're able to continue doing operations until before you have received all of your information. Okay. Now this is one of the issues today. Is that on the other hand, computer architects say we're going to give you sequential consistency, but we really want relaxed. Okay. Now the reason for that is that the computer architects say that implementing sequential consistency, okay, which I know these are just kind of words right now, but they're different extremes with different memory models. One view of the memory model is sequential consistency. The processor designers say that it will take exponentially more transistors as core counts increase to have that model, right? Whereas a relaxed model is very fast. So if you are doing high performance computing, you have no choice but to use relaxed memory models because they are blazingly fast and they will continue to scale for a long time. So I'm not going to go into a lot of detail in terms of exactly how the models work. To do that will take several days, right? However, we do have these two very disparate notions, and I will show you some. I think I have an example in here. If I don't, I can pull it up. We're having some pizza to show you how nasty things can get. And software engineers just are tired. They're probably running out of the room right now and saying, like, seriously, just lock things, right? So, one view is that memory models aren't important. We have it all figured out. Doesn't affect us, etc. But where we are right now, today, is that we have several equivalent. We have definitions for how equivalent programs work. It's math, so we have partial orders, total orders, sets of sets, permissional execution. It's about 45 pages of just density, laying down definition, 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 definition. Suppose you have this definition, and it winds up just showing you the possible interleavings. So in a sequential system, it's really easy. I have variable x. Unless I touched variable x, nothing touched it, right? It cannot have changed. Now in a parallel system, it could have changed. And it could have changed by many possible actors. So rather than looking at variables as a box of memory, in a parallel system, you're actually looking at it as a sequence of memory that has many possible values at any given point in time. So when we talk about equivalency, we actually are having a very large set of possible outcomes, or every possible way the processor could have executed it. And we need to make sure when we design algorithms that every possible execution in that set is okay. It's completely valid. Otherwise, your program may not work properly. And the reason I'm not showing the detail is no one's ever going to understand this stuff, right? This is extremely complicated, right? People doing high performance computing have to, because we're trying to model things. We're trying to actually build interesting applications and do science. So we're going to have to go through and try to figure out how to make it work right now while we're getting those high level abstractions, right? So we're in a situation that parallel programming is already hard, and now the memory model makes things a lot harder, right? So it's kind of a sad state that parallel programming we're still figuring out, and now I'm throwing on you, we have this memory model that makes your life even more difficult, right? And really, if you think about it from a scientific perspective, this is no different than general relativity. The world gets more complicated as you get more accurate, right? I think we all know that. General relativity is correct, but I don't think you're going to see many engineers employing it in their day-to-day life when they're building a bridge or a skyscraper or something like that, right? And this is an interesting quote from Mike Wong. He says that actually general relativity is easier than this stuff. So this is why, I mean, I don't think you would start a first-year physics lecture with general relativity, right? So this is why I'm not going into a lot of details of the models. It is very, very complex. I'd have to assume a lot of background or give you the background and prepare you. So where we're going in terms of this stuff is to make this problem go away. The goal of computer science today is to provide you with higher level constructs. So what that means is, if you think of it, from the perspective of a computer, there is no such thing as a for loop, an if statement. None of that stuff actually exists. It's all compiled. It's an artificial construct that's compiled to the ISA. That's where, in my opinion, everything is going, is that we're going to have something that inherently allows composition or these types of things. We just don't know what those are yet, right? Once we have those, hopefully these memory model problems can go away, because when we have those constructs, they've been designed to adhere to that model. You throw them in your language, and a lot of these issues disappear. That's probably where things are going to go. But we have to be at this level right now that we're making sure that all the pieces are fitting. And then once we do that, we can actually build the high level constructs. So the memory model right now, the OpenCL memory model I showed has some problems. Okay, and not just the OpenCL memory model, all the memory models have problems. But what's nice is that we're finding them. So as we actually find issues, we're practicing science. We say, okay, this is a problem. You publish a paper, it gets ignored. You go talk to the person that says, oh, that is a problem, right? I think we're all familiar with a little bit of the current state of papers, right? So you basically can put together, you can say, okay, this is a problem. We're going to fix this. Tell them, and it actually gets repaired, published, fixed forever, right? This is science. It's completely open. Everyone's working on this, contributing around the world. And there are today popular parallel programming languages and frameworks that actually have no memory model. They're not even described. They're just hoping you don't notice. So I would caution you against using such things, because it means that you're in kind of this shaky foundation where you don't really know how your data structure is going to behave, if that makes sense, right? So even though it's complicated, it's important to understand how it works and why it works the way it does. So once we have this piece, we can go back to what we actually want to do, which is solve parallel programming. So we kind of taken this long detour as an industry to firm up what happens literally when you have a concurrent read and write to the same memory location. Once we have that determined and what's going to happen, which is the result of the memory model, how things behave as things operate, now we can go back to, okay, how do we make this stuff disappear? And that's the state of where we are today. So if we really want to get into the deep details of this, I mean, we've already been about 50 minutes into just kind of a basic discussion. We're just motivating. If we want to get into the details of relationships, it's going to take an entire course. It'll take several days of a course. So one of the things I do is I do provide training. I've been speaking with Marcelo and others about doing something for training for people who actually want to learn the memory model in detail. Learning the memory model, I mean, you would have to learn parallel programming first, and that's about 3-4 days. To actually learn the memory model would be another 3-4 days, right? So you really, maybe something interesting to talk to about Science is building a course on this whole material from end to end, right? So I don't do hocus pocus stuff, but I can teach you what we know, what we don't know, and then figure out how we use these pieces. We can teach science here. I did give training at the Fields Institute, specifically for members of the academic community. And this was done at the beginning of February, I believe. I do have a nice little, Mike Wong, who's a CEO of, former CEO of OpenMP, gave me a nice little testimonial I'll show you. In terms of academic training, I will be offering some training, probably at a hotel downtown type of thing for a few days. We'll actually go through and detail a lot of this type of stuff. And you can always talk to me. I mean, I'm not here to charge academia millions of dollars, so we can probably do something discounted for starving students who are just trying to get out, but actually want to dig into the memory model. It's probably more interesting for members of SciNet to really get into the details of the memory model and then advise and train other people who are the users, right? So as a user, you really don't want to deal with this stuff, right? You really want this to go away. But someone can show you little guidelines and say, look, in general, this is a problem, but for your problem, obey these rules, you're fine. That's the type of advice you need. I need to talk to your friendly two computer scientist for that. So this is a nice little thing that Mike Wong sent. I'll put it up after we finish the broadcast. You can take a look and a couple references. And yeah, so now we can answer questions. Hopefully it's not, I know that it's not what you might expect in terms of going into the nitty gritty, but this is exactly how it works because it would be way too much. So please feel free to ask questions, and that's it.
I still have the question, what is a memory model? I don't understand that.
So
as a definition of what you mean by a memory model. Is it just
it's
the three rules that you need?
It's a formality. So it's a formalized system that actually gives you the rules. So it says, suppose that X is a variable of such and such form. It is not permissible that such and such transformation may occur. However, these transformations may occur. In this case, this happens. So it's a complete formalized system. It's basically written very mathematically in terms of sets and so on. It says, this is the definition of how memory behaves under all possible situations. And then these are the valid transformations that can be done. Does that make sense? We can open up the PDF and actually show you if you'd like, can you open up the
No, I don't need to read the math. Just, conceptually, that's what you mean by a memory model.
That's right. It's a formal system. So no different than anything else. This is like Newton's 3 laws, right? This is how it behaves, and you have all the surrounding stuff. Here we say this is how memory behaves under these operations. And then you can, the goal of doing that is that you can prove that your algorithm that you believe should be correct actually is. And you can't prove that unless the compiler agrees that it has not violated that promise, and the processor agrees it has not violated that promise. So the reason this complexity actually exists is to prove formally that what you think operates as a mutex is a mutex under all possible situations, as an example. But rather than just standardizing mutexes, we standardized all of the other pieces to make a mutex so that you can make whatever you want. Does that make sense? Because we don't want to just force you into one abstraction. So hopefully that kind of makes sense.
So some of your examples would turn out to basically be invalid.
Which ones?
Like your example where Y was set, was rearranged.
Yes, the memory model says that is not legal.
So, but there must be a way to express that in the way you sort of intended, right? So rather than having memory said you can't do that, there must be something that comes. Well, you have to express it such that
yes,
you put a barrier or something similar there.
Yes. So you actually get two pieces. You get atomics and you get fences, and then it describes how those things interoperate. But fences are parameterized by the model that they expect. Same with atomics. So you can say this fence at one extreme is a sequential fence, or this is a relaxed fence. Then what it describes is the high-level function that just says lock actually implies an ordering for everything below, and the unlock applies an ordering for everything above, right? So it allows you to actually specify this is the behavior of memory in between. Otherwise, the reason it doesn't work is there's no formalized system. Another way of thinking of it is that the memory model is a set of constraints that say any valid program is constrained to have these behaviors. And then how you use that is like anything else. It's like saying, this is an if statement, this is a for loop, what do you do with it? Well, you can do lots of things. That's exactly the situation of the memory model. We're giving you the pieces.
So in a sense, what you're saying is, tell the compiler writers that they should make sure that the code they generate produces something valid while still keeping the language as the language that it always was.
Yes, and that's why the C++ language, for example, if you don't use parallelism, it just works. The memory model is what you think. It reduces to exactly what you believe, right? If you start to use parallelism, the memory model starts to turn on. But if you just use features like locking and unlocking, it just works out of the box. But these are exposed so you can make other things on top of it. Other questions? Those are online questions. Yeah, sure.
So one of our viewers mentioned the PowerPC example when you mentioned compositability, that you have instructions that you can do composite operations, say bit by bit and add or something like that.
So the general issue with composability is
specifically for PowerPC.
Yeah, so I can give you the general answer in terms of what goes wrong, and then you can extrapolate it to PowerPC. So in general, what goes wrong is that in terms of composability, one, you have different models. Okay, so if I have something that is a parallel framework, like say OpenMP or TBB or one of these frameworks, they expect that they're the only thing running on that processor. If I call a different function that's written in a different framework, they either don't work at all because they interfere with each other, or if they do work, they're so slow that that's not why you did it in the first place. So that's one solution. The other answer is, counterexample is, I might have a function that requires a certain mutex, and the order of the calls violates the locking, right? So that would not necessarily happen in, think of it this way, you wind up having almost a global state, right, when you have a parallel system. And how you interact with that global state can change based on which function executed first, right? That makes sense. I mean, there are examples. There's in the references, I believe I cited where that comes out of, this reference, structured parallel programming. They go through that, as well as the book from Hilarhi on the art of multiprocessor programming. I believe he actually gives you a proof for a counterexample.
The other comment I have, and this is personal mine, right, is I think it's too strong to say that parallelism doesn't work, right? I mean, I have been running, and many other people here have been running parallel codes, scaling up to 100 of cores or so, and we get solutions that make sense, that are consistent. So I understand that there may be special cases where this breaks down, but saying in general that parallelism doesn't work, I think it's too strong.
Well, I think that it's like saying that Newtonian physics doesn't work. Sometimes it will, sometimes it will not.
Well, it's a limit, right? Taking your example of general relativity, Newtonian physics is a limit of the theory, right? So it's not completely incorrect.
So what I really want to get at is that the concept of parallelism and the concept of how memory behaves are so tightly intertwined that you actually can't separate the two. And parallelism we've been playing with. Memory, we didn't really have a good foundation. So in order to make sure that your algorithm is correct right now, that you've been practicing, without the memory model, you actually have a memory model, you just don't know it. You have it in terms of the instruction set of the actual processor. We'll say, this is the behavior of this operation upon this memory cell. But they've been different, and they weren't really the same. So you might run something on PowerPC, you might run something on Cell, you might run something on x86. Each of these has a memory model. These memory models actually have existed, but they were only in the ISA level. But you weren't guaranteed that the compiler and the processor actually connected or ran the program you think. So for your example, you may not have known about the memory model, and it may have just worked for you because the compiler writers tried to make sure that it would, right? But what it limits is your ability to make high-level frameworks or other approaches to parallelism, if that makes sense. So when I say it doesn't work, I'm speaking in the pure mathematical sense of it, that I can always show you counterexamples where it's going to break. And I would argue that actually you had a memory model already, it just you didn't have a very nice one. You had the ISA and you had to understand exactly the order of instructions and so on.
Even when you use instructions, let's take MPI for example, and you try to control the execution order of the threads or the processes.
Mm-hmm.
You think that is even still risky because there is no memory model underlying?
Well, if you compiled with C or C++, C or C++11, you have the memory model there. The memory model was already something was already in existence. And the people who wrote these frameworks were generally very careful. Where this comes in is honestly when you want to prove that what you did is actually right. So the people who implemented those frameworks would have had a very, very hard time to actually make sure it was completely correct. They had to look up the manual for every single architecture, right? Check the ISA and make it completely sure.
When you look at the details, things like MPI specs, it will tell you, for instance, that when you send a message, you can't trust that you can change the buffer unless you explicitly buffer it. So the memory model is in some sense very relaxed. That doesn't guarantee you much. They'll put a barrier or something, which of course will solve.
But you can do, that's my point. You can do, I mean, it's up to the programmer.
Yeah, no, exactly. So in essence, you're getting this fairly relaxed model to some extent. And it's in the spec system. You can't trust it. Often so if you're not careful to make sure that when you need to reuse that buffer, there hasn't been some implicit or explicit buffer, it could happen that things on. And this could be one of those 99% of the times it does work. 1% where the messages took a little longer.
Right.
So, but a a lot of cases you program in a way where there is some implicit buffer. You have the time stamping, everything has to be done as a certain level. Might be mild in terms of your.
Well, this is a message passing system, right? So this is specifically talking about shared memory.
No. I think like when you pass this message to the library, the internet library, you just get a pointer to the memory address that's supposed to be sent, right? So unless you do like a secure send or something, or even worse, you're not supposed to touch the original buffer until you have somehow verified that the message has arrived.
Well, there's a few interesting points with reads and writes, right? You can think of the memory model as a message passing system if that's easier for you. They're actually emitting from one processor a set of reads that you're waiting to collect and a set of writes. In relaxed, those commands can be completely reissued. It actually is possible to write a value before you read it, right? So you actually can play with, the reason that this is more difficult than general relativity is that messages can go travel through time. Right? That's not expected, but the processor can do advantages where something's not globally visible and so on. So the memory model.
Still don't agree. This is more difficult than general relativity.
Well, I mean,
independently of that, you also mentioned.
You can mention to Mike Wong. So Mike Wong did his original training here as an astrophysicist, and now he's gone off to this. So I'm using this is his quote, not mine.
I think that's fine.
If you're interested, I asked him for the exact reason, and he actually gave me the astronomy ease. So I will read you exactly why he said it is more difficult afterwards.
Okay, but at some point you mentioned also that you can translate basically between shared memory and message passing algorithms, and the problem will still be there, right?
Yeah. Yeah, I mean, from a computer science standpoint, they're equivalent, right? I can implement message passing in terms of shared memory, and I can implement shared memory in terms of message passing. So anything I prove about one system will hold on the other. I just do the transformation and say QED. Does that make sense? So in computer science, it's often how we think of things. This is a problem in general, and then this is the behavior, and I know that these concepts are equivalent. So I can give you a counterexample in either.
So do you think this problem is more likely to show in cases where you have heterogeneous computing or multiple devices?
Well, it happens anywhere you have parallelism. Even if you only have two units of execution, it's going to happen. It's an inherent property of the system.
There is no more chance that happens in a particular architecture.
Well, the thing is that it's undefined, right? So when I say the data rate, so in order to violate the memory model, okay, you have to have a data race. You have done something that has caused a data race. Now you're in violation, right? So, it is saying like this is basically, I mean, maybe this is a better thing for Danny. The way to say the memory model is that you cannot have a data race. And here's all the constraints to make sure it will never happen. These are the rules. The objective is this can never happen. And these are all the rules. If you do this, this is how you get a data race. And that's not possible, right? So the issue is that let's say that the guarantee is that data races never occur, and you're building a memory controller. You might actually use the fact this is completely undefined to do something that you don't even know how it's going to behave. There is no logic because it can't happen. And if it does happen, it should not have, right? So this is why it's so dangerous, is that people say, but this is what's going to happen. Because it's undefined, the processor people, the architect people, the memory people, any of them at any point can use this information to give you more performance, because the people who have not violated the memory model may see their programs execute 30 times faster because they just say, well, if you have a race, this isn't our problem. And I don't even know what's going to happen.
I think it's the point that is counterintuitive to me, because usually if I see a race condition, it's probably because I did something wrong in my code, right? But I can look at the algorithm and I can say, oh, this is my mistake because I was either not sending the data safely, or not blocking, or not waiting for other processes to come back and combine the data. I don't think it as a hardware problem itself, or a standard problem, design problem.
If you are writing your code to just use locks, so I'm going to sum forces on something, and to do that, I'm just going to lock the term with the summation. I'm just going to add them one at a time. You're not violating the memory model, but you also aren't benefiting.
Right. But
if you implemented the same thing in relaxed consistency, that summation may be many, like 200-300 times faster, right? Because you're getting more parallelism because a mutex blocks out every single thread, right? And then you're using relaxed, which allows all sorts of reordering tricks. So if you just lock and unlock and so on, like, yeah, that can be the memory model that you employ. But the reason that the more advanced ones are there is if you use them for your advantage, you can get a lot more performance. Does that make sense?
The thing is today, the onus is on the programmer even at high level. And if things were implemented at a low level and always obeyed, then you stand a better chance of the compiler and those tools helping you out and not having to worry too much, when you're programming at high level. That's the way I see it.
Yes, there's examples even in the Linux kernel where the memory model kind of messed them up, right? Where they compiled things and they weren't following the memory model correctly. So a good example is once ARM devices are more relaxed than Intel processors. Intel processors are actually pretty friendly in terms of how they manipulate memory. The alpha was the worst of the worst in terms of how it does anything, right? So alpha, actually the Linux kernel is designed assuming an alpha processor because it's the most crazy processor they can find. So they figure if it'll work on alpha, it'll work anywhere. But it had never been, exactly, because of relaxed. That's one of the reasons, right? So once you take what happened is these things had never been tested. They run on ARM and big parts of the Linux kernel just broke, right? Because they had never been tried there. And again, like the memory model is an inherent property of parallelism. So here we're talking about HPC and users, but it affects the operating system. Sure. It affects absolutely everything. And the reason it's defined now is it can be used by computer architects, it can be used by everyone, and there's a promise that this is going to be obeyed. In terms of taking advantage of the memory model versus ignoring it, if you actually leverage the memory model, you can write code that is orders of magnitude faster than others who did not. And that translates into removing nodes, right? Reducing resources. So in many ways, I mean, if you didn't, the memory models have kind of always been there. This is one where you have formalized that everyone has agreed to what it should be, right? So every processor vendor had a different idea in terms of what memory should look like. The advantage of what's happened is everyone's come together and agreed this is how it should be. Now, because of that, we have a couple different models that exist, but they're still standardized, and every processor vendor in the world has agreed this is how they're going to work. From an FPGA to a CPU to a GPU. It's actually kind of surprising in a way that the standard now is that all of these devices with completely different architectures, completely different methods of operation are going to work in the same way. Does that make sense? Any other questions or?
You managed to bewilder everybody.
Well, at the end of the day, it's making sure that things actually work the way you expect they work, right?
Do these references say anything about this memory model that was agreed on?
They certainly do. The best place to find the memory model is the OpenCL 2.0 spec for that one. HSA has a memory model, and OpenCL has a memory model. And that's kind of, yeah. So the art of multiprocessor programming only deals with sequential consistency, so it has a lot of algorithms that won't work in relaxed. The memory models are discussed on 2 pages here in the structured parallel programming. And computer organization and design is mostly talking about cache effects and so on. I won't describe the memory model. In terms of where do you find the memory model and where do you actually learn it, you don't. The only place to learn it is through a collection of papers and the formal specification. There are no resources that make it bite-sized. Does that make sense?
No, it's okay. It's a fact.
Yeah, I mean, let's say that I was coming here and I said, look, I have the whiz-bang product. And Marcelo here says, okay, great, we have the whiz-bang product. I have a new way that I'm going to sum up forces because it's going to be faster. And Marcelo has no idea if it's going to work or not, right? And they don't either, the people who implemented it. So the whole point of doing this exercise is to make sure that things work the way you expect. They may be very confusing, but as users, you will never be confused because a person who designed the library, who designed the compiler and designed the hardware, all made sure that it worked for you. But if you didn't have those things, all bets are off. So it's an important piece that has to be there. No different than an ISA. How many people program in assembly language anymore? How many people believe that assembly language exists? Yeah, it has to be there. The memory model has to be there, just like the instructions have to be there. Doesn't mean you have to use it. Just means it must be there. Okay, so if you have any more questions, I guess, I don't know if you've already stopped broadcasting, we can just,
We have 2 questions.
yeah. Any final questions? Otherwise, we'll have pizza and have more interesting discussion at the board type of thing.
Yeah, probably there is something more pizza.
Well, thanks. you.
Yeah, I'm glad we can bewildered everyone. But.